A very good morning to all of you. Myself Deepti Jain, lecturer in electrical engineering from GPC Kunimajra, and I am here to present a lecture on magnetic materials. So first of all, introduction. What are the magnetic materials? So magnetic materials are those substances which are attracted by a magnet and which can also be made into a magnet by using some techniques. So main examples of magnetic materials are iron, cobalt, nickel and gadolinium. Next is, what are the main properties of a magnet? So first, for every magnet there are north poles and south poles. Like poles repel each other and unlike poles attract each other. Means the same poles always repel each other and the different poles always attract each other. Third is, magnetic forces attract only magnetic materials and the magnetic forces act as a distance. Means and the last is, the while magnetized, the temporary magnets acts like a permanent magnet. The next is, for every north there is a south. So we have a small example, like every magnet has at least one north pole and one south pole. Now by convention we can say that the magnetic field lines leave the north end of the magnet and enter the south end of the magnet. So suppose this is a bar magnet, एक अपने को एक bar magnet है, जे आपा इस बार मैगनेट दे एक पोल जिहड़ा होएगा नॉर्थ पोल होएगा तो दूसरा पोल जिहड़ा होएगा इट विल बी अ साउथ पोल. ठीक है, एंड जिहड़ियां भी मैगनेटिक लाइन्स ऑफ फोर्स हैगियां ने इट विल लीव द नॉर्थ एंड एंड इट विल एंटर फ्रॉम द साउथ एंड. So if you take a bar magnet and break it into two pieces, each piece will again have a north and south pole. So suppose this is a bar magnet and we have cut it into two pieces, then again for these two pieces again we have north and south pole, north and south pole. So again if you take one of those pieces and break it into two, each of the smaller pieces will have north pole and south pole. जे ਆਪਾਂ इस मैगनेट ਨੂੰ ਫਿਰ ਦੁਬਾਰਾ ਕੱਟ ਦਈਏ ਤਾਂ ਫਿਰ ਜਿਹੜੇ ਵੀ ਦੋ ਹਿੱਸੇ ਆਪਣੇ ਕੋਲ ਬਣਨਗੇ ਉਹਨਾਂ ਦਾ ਫਿਰ ਨਾਰਥ ਤੇ ਸਾਊਥ ਪੋਲ ਡਿਵੈਲਪ ਹੋ ਜਾਏਗਾ. So no matter how small the pieces of the magnet become, each piece will have a north pole and the south pole. So for a magnet there is no any monopoles. So next slide is, no monopoles allowed in a magnet. So it has been shown to the possible to end up with a single north pole or a single south pole which is a monopole. So कोई भी magnet इस तरह दा नहीं है कि जिस उत्ते सिर्फ ही एक single या तो south pole होवे या फिर north pole होवे. So the monopoles are not allowed in the magnets. Now all the magnets have a magnetic field. Now we can say that a moving charge set up in the space around it a magnetic field, and it is the magnetic field which exerts a force on any other charge moving through it. So these magnetic fields are the vector quantities, and that is they have a magnitude and direction. So let us revise the previous slides. Magnetism basics. So a magnet is associated with magnetic lines of force with a north pole and a south pole. The lines of force come out from the north pole and it enters from the south pole. So a current in a ring or coil also produces magnetic lines of force. So basically the magnetism arises from the magnetic moment, or you can say magnetic dipole of magnetic materials. So basically ਜਿਹੜਾ magnetic movement है ਹੁੰਦਾ ਕੀ ਹੈ, ਇਹ basically ਦੋ ਤਰ੍ਹਾਂ ਦਾ ਹੁੰਦਾ ਹੈ. First is orbital magnetic movement and second is spin magnetic movement. So first of all let us discuss what is orbital magnetic movement. So when the electrons revolves around the nucleus, then it is known as orbital magnetic movement. Now next is spin magnetic movement. Now when the electrons spin, then that magnetic moment is known as spin magnetic movement. So जब भी इलेक्ट्रॉन न्यूक्लियस ਦੇ ਆਲੇ ਦੁਆਲੇ ਰਿਵੋਲਵ ਕਰਦਾ ਹੈ, ਜਦ ਉਸ ਤੋਂ ਜਿਹੜਾ ਮੈਗਨੈਟਿਕ ਮੂਵਮੈਂਟ ਅਰਾਈਜ਼ ਹੁੰਦਾ ਹੈ ਉਸ ਨੂੰ ਆਪਾਂ ਬੋਲਦੇ ਹਾਂ ਆਰਬਿਟਲ ਮੈਗਨੈਟਿਕ ਮੂਵਮੈਂਟ, ਅਤੇ ਉਹ ਮੈਗਨੈਟਿਕ ਮੂਵਮੈਂਟ ਜਿਹੜਾ ਕਿ ਇਲੈਕਟ੍ਰੋਨ ਦੇ ਖੁਦ ਦੇ ਸਪਿਨ ਹੋਣ ਦੇ ਨਾਲ ਪ੍ਰੋਡਿਊਸ ਹੁੰਦਾ ਹੈ, that magnetic movement is known as spin magnetic movement. The permanent magnetic movements can arise due to, the first is the orbital magnetic movement of the electrons, the second is the spin magnetic movement of the electrons, and last is the spin magnetic movement of the nucleus. The next is, let us discuss the main characteristics of any magnetic material. So these are the some properties of a magnetic material. The first is magnetic permeability, second is coercive force, third is magnetization curve, fourth is retentivity, fifth is hysteresis and hysteresis loss, next is Curie temperature, seventh is eddy current loss, eighth is demagnetization curve, ninth is magnetic field intensity, 10th is saturation constant, 11th is the hardness constant, and the last is magnetization phenomena. So these are the some characteristics of any magnetic material. So let us discuss all these characteristics one by one. The first is permeability. Now permeability may be taken as the magnetic conductivity. So it is the ability of a magnetic material to conduct the magnetic flux through it. It is known as permeability. Now it is similar to the conductivity in case of the any electric material. So soft iron is a very good conductor of magnetic flux, and the permeability of the air, vacuum and other non-magnetic materials, it is very poor, and almost all have the same value of the permeability, and the value for the air or vacuum is generally constant, and it is 4 pi into 10 raised to power minus 7 Henry per meter. So we can say that what is permeability? It is just the conductivity of a magnetic material. The next is relative permeability. So it can be defined as the conducting power of the substance for magnetic lines of force as compared to the air. So if we compare the conducting power of any substance with respect to the air, then that is known as relative permeability of that material. So we can also define as the it is the ratio of permeability of any material which is represented as mu to the permeability of air or vacuum which is represented as mu naught. So it is known as relative permeability. So mu r is equals to mu upon mu naught is the relative permeability. The next characteristic of a magnetic material is coercive force. So it is the magnetizing force in the opposite direction to wipe out the magnetism completely is known as coercive force, and it is also defined as the demagnetizing force. So this red point, now from this point to this point, this is known as coercive force. So when we apply the magnetizing force in the opposite direction to wipe out the magnetism completely, then that force is known as coercive force. So from this point to this point, this is known as coercivity. So this is a hysteresis loop. Now next is magnetization curve. So this is the curve which shows the relation between the magnetic flux density B and the intensity of magnetizing force, that is H. So if we plot a graph between B, that is the flux density, and H, that is the intensity of magnetizing force, then that curve is known as magnetization curve. So it is also known as BH curve. So the ratio, that is B upon H, or the slope of the curve, represents the relative permeability of the material. So see, if we draw slope of for this curve, then that is the relative permeability, and the curve rapidly at the start showing a big change in the B with relatively small magnetic field intensity H. So then as the value of H is increases, flux density B rises, and hence the relative permeability increases. So if we see this curve, for start, as we increase H, B starts increasing. So for again, as we go on increasing the H, the B starts increasing. Now after a point, this point is known as knee point. So at this point the curve starts, as we increase H, the value of B is increasing. Now next, if H is increased above the knee portion, so this is the knee portion, ਕਹਿੰਦੇ ਜੇ ਆਪਾਂ ਇਸ ਤੋਂ ਵੀ H ਦੀ ਵੈਲਿਊ ਨੂੰ ਇੰਕਰੀਜ਼ ਕਰਨਾ ਸਟਾਰਟ ਕਰਾਂਗੇ, then the curve tends to become horizontal. ਜਿਹੜੀ curve ਹੈ ਇਸਨੇ horizontal ਹੋਣਾ start ਹੋ ਜਾਣਾ ਹੈ. Now indicating very slight change of the flux density, and hence permeability decreases. And a stage is reached when the slope of the curve becomes constant and the value of mu r is equals to mu naught. So this condition is known as saturation, and here we have taken H in ampere turns per meter and the B in Webers per meter square or Tesla. So see, initially as we increase the H, value of B increases. So there is a rapid increase in B with the increase in H. So after this knee point, as we increase H, the curve becomes horizontal, means there is a slight change in B with increase in H, and after some time the value becomes almost constant, that is the relative permeability becomes equals to the permeability of the free space. So this condition is known as saturation. Now next is retentivity. Now if a soft iron piece is magnetized by induction and then the inducing magnet is removed, the soft iron piece will immediately lose its induced magnetism. So but on the other hand, if a hard steel piece is magnetized by induction and again the inducing magnet is removed, it will be seen that the steel piece will retain magnetism for some time. So this property of retaining the magnetism after the inducing magnet is removed is known as retentivity of the material. The next is, what is magnetic flux density? So the magnetic flux density is defined as the number of lines of magnetic force passing through unit area perpendicularly is known as flux density, and its units is Weber per meter square or Tesla. And what is the magnetic field intensity? is defined at any point in the magnetic field is the force experienced by an unit north pole placed at that point is known as field intensity. So, its unit is ampere per meter, ampere turns per meter. The next is hysteresis. Now, hysteresis is a phenomena of lagging behind of flux density B to the magnetizing force H in a magnetic material is known as magnetic hysteresis. So, see, this is a iron bar. Now, see, this is a loop, this is known as hysteresis loop. Now, this has been drawn between the flux density and the field intensity. Now, see, in the start, as we increase H, B increases. So, with the increase in H, there is a rapid increase in B. So, after some point at the knee point, as we reduce the value of H, जो B है, it will not reduced from the same path, but it follows some another path and it meets at y axis at this point. So, from O to B, this is known as retentivity, means ਆਪਾਂ magnetization ਨੂੰ remove भी करता, but still there is a magnetization for that material. So, this power of retaining the magnetism is known as retentivity. So, OB shows the retentivity. Now, we again reduce the magnetic field intensity in the reverse direction, then this is known as coercivity, OC. So, again reducing, and this follows the closed path and this is known as hysteresis. So, if a sample of ferromagnetic material initially in a completely demagnetized state is taken through a cycle of magnetization in which the magnetizing force H is increased from 0 to the maximum, then decreased from 0, then reversed and again taken to the maximum and finally brought to 0, the variation of flux density B with magnetizing force H will be represented by a closed loop is called the hysteresis loop. So, see this curve, firstly it is increasing, then decreasing to a negative value, again increasing, then to the 0 and then again increasing. So, this closed loop is known as the hysteresis loop. So, this is a hysteresis loop in which we have defined the various quantities. So, this is the saturation point, O Mr is the retentivity, R Hc is the coercivity. So, if we start with no magnetized specimen, that is M is equals to 0. Now, with the increasing value of magnetizing field H, the magnetization of the specimen increases from 0 to higher values and attains its maximum value at a point P. So, from as we increase this H, B increases and attains the maximum value P. At this point, the magnetization referred as saturation magnetization. So, at this P point, this is called the saturation point, where the curve becomes almost constant. Now, this is the knee point. Now, when we increase magnetic field H, there is no further increment in the magnetic moment. So, after this P point, as we increase H, there is no any increase in the magnetic moment, and when we decrease the magnetic field H to 0, the magnetization M attains the point Q. So, as we increase the decrease the value of H, then it will attains the point Q. So, from 0 to Q, this state is known as retentivity. So, at this point magnetization referred as residual magnetization or MR. So, further if we increase the magnetic field from 0 to negative values, the magnetization of material becomes 0 at a point R. So, this is a point R where magnetization becomes 0. So, at that point the magnetic field at C is referred to as coercivity of the specimen. Now, if we increase magnetic field H in the reverse direction, the magnetization of material reaches its peak value at a point S. So, if we again increase the value of H, then again saturation point achieved, but in the negative direction. So, on reversing the polarities of a magnetic field and increasing its strength, the magnetization slowly decreases, first to residual value, then to 0, and finally increases to saturation state and touches the original saturation curve. So, the area of the loop indicates the amount of energy wasted in one cycle of the operation. So, with this, firstly increase the value of H, then decrease, then again we have removed again increase in the negative direction, again it will meet the same point. So, this is known as the closed loop or hysteresis loop, and it indicates how much energy has been wasted in the one cycle of magnetization. So, let us discuss now what is the hysteresis laws. Now, for establishing the magnetic field, energy is required, as you know. So, this setups the magnetic field in the free space, then energy is stored and returned when the field collapses. So, but if the material is magnetic, then all the energy is not returned, whereas a part of this energy is lost in the form of heat and it heats up the magnetic material. So, this is known as the magnetic material, and the energy waste in the form of heat is known as hysteresis loss. So, the hysteresis loss depends upon the following factors. First is the area of the hysteresis loss loop. More the area of the hysteresis loop, more is the hysteresis loss. Now, second is frequency of reversal of magnetism. So, greater is the frequency of reversal of magnetism, greater is the hysteresis loss. Now, third is volume of the material. Greater the volume, greater is the hysteresis loss. The next is Curie temperature. So, it is defined as the temperature at which ferromagnetic material lose their magnetic properties is known as Curie temperature. Now, fifth is it depends upon the eddy current loss. Sixth is it depends upon the retentivity. So, it is defined as the property of a magnetic material to retain the magnetic properties after the magnetizing force is removed. The next is coercive force. So, it is the magnetizing force acting in the opposite direction to wipe out the magnetism completely. So, more is the retentivity, more is the hysteresis loss, more is the coercive force, more is the hysteresis loss. So, all the factors are directly proportional to the hysteresis loss. The next is, let us define what is eddy current loss. Now, similarly, when iron parts are subjected to varying flux, the currents are induced in them due to the electromagnetic induction. So, these are called the eddy currents, and these eddy currents induced in the iron parts result in the loss of power and heat the material. ਸੋ ਆਪਾਂ ਕਹਿ ਸਕਦੇ ਹਾਂ ਕਿ ਇਹਨਾਂ ਐਡੀ ਕਰੰਟਸ ਦੀ ਵਜ੍ਹਾ ਦੇ ਨਾਲ ਜਿਹੜਾ ਆਇਰਨ ਦੇ ਪਾਰਟਸ ਵਿੱਚ ਬਹੁਤ ਹੀ ਲਾਸ ਹੋ ਜਾਂਦਾ ਹੈ ਅਤੇ ਇਹ ਆਇਰਨ ਨੂੰ ਗਰਮ ਵੀ ਕਰ ਦਿੰਦਾ ਹੈ। ਸੋ ਬਿਕੋਜ਼ ਆਫ these ਐਡੀ ਕਰੰਟਸ this loss is known as eddy current loss. Now this loss of power is known as eddy current loss, and these losses can be reduced by making the core in the form of thin sheets, that is the laminations of the iron insulated from each other by layer of varnish. So ਆਪਾਂ ਇਸ eddy current loss ਨੂੰ minimize ਕਰ ਸਕਦੇ ਹਾਂ if we ਜੇ ਆਪਾਂ ਜਿਹੜੀ ਵੀ ਕੋਰ ਹੈ ਉਹ ਥਿਨ ਸ਼ੀਟਸ ਦੀ ਬਣਾਈ ਜਾਵੇ ਇਨ ਦ ਫਾਰਮ ਆਫ ਲੈਮੀਨੇਸ਼ਨਸ ਅਤੇ ਹਰੇਕ ਲੇਅਰ ਦੇ ਵਿੱਚ ਵਾਰਨਿਸ਼ ਕੀਤੀ ਜਾਵੇ। ਜਿਹੜੀ ਹਰੇਕ ਲੇਅਰ ਹੈ ਦੈਟ ਇਜ਼ ਇਨਸੂਲੇਟਿਡ ਫਰੋਮ ਈਚ ਅਦਰ ਬਾਈ ਦ ਲੇਅਰ ਆਫ ਦ ਵਾਰਨਿਸ਼। ਸੋ ਦ ਐਡੀ ਕਰੰਟ ਲਾਸ ਕੈਨ ਬੀ ਰਿਡਿਊਸਡ ਬਾਈ ਯੂਜ਼ਿੰਗ ਦ laminations. The eddy current losses are proportional to B maximum square F square T square, where B is the flux density, F is the frequency and T is the thickness of the thin sheet lamination. The next is reduction of how we reduce the hysteresis loss. Now hysteresis loss is directly proportional to B maximum FV, where K is the constant, hysteresis constant. So hysteresis loss can be reduced by using high grade magnetic material, that is silicon steel. So if we use the silicon steel for making the core of the machine and transformer, then the hysteresis loss can be minimized. Now next is how we can reduce the eddy current loss. Eddy current loss is directly proportional to flux density square, frequency square and the thickness of the sheet, where K is the constant, that is the eddy current constant, and it can be reduced by making the cores of the machine of thin laminations. So in this way we can reduce the eddy current loss. Now next is the classification of magnetic material. Basically the magnetic materials can be categorized into two types: magnetic materials and the non-magnetic materials. Magnetic materials can be written as ferromagnetic materials. Now again these ferromagnetic materials are again of two types: soft magnetic materials and hard magnetic materials, whereas the non-magnetic materials is of two types: paramagnetic materials and diamagnetic materials. So let us discuss all of these type of magnetic materials one by one. Now the classification of magnetic materials. Now all the materials can be classified in terms of their magnetic behavior, falling into one of the 5 categories depending on their bulk magnetic susceptibility. Now magnetic susceptibility can be defined as the degree of magnetization of a material in response to an applied magnetic field is known as magnetic susceptibility. So the two most common types of magnetism are diamagnetism and paramagnetism, which account for the magnetic properties of most of the periodic table of elements at room temperature. So see, this is a periodic table in which we have classified the 3 categories. First is diamagnetic, paramagnetic and the ferromagnetic material. So diamagnetic material in the purple shade. So all the non-metals except oxygen, and so these are the diamagnetic material, and all the metals except iron, cobalt and nickel, these are the paramagnetic material. So you can see for the ferromagnetic material we have only 3 materials: iron, cobalt and nickel. So, these are the materials which have magnetic properties. So, classification: